All right. So for question 1 here regarding for problem set 2b, which is what's a spectral leakage and how the effects can be reduced in practice, what we're looking at in particular is in the spectral leakage lecture. We want to actually observe what spectral leakage is regards to explain this question. So what happens is that spectral leakage occurs when we're trying to sample regards to our original signal. And once the signal bins does not correspond, once the sample frequency bins does not correspond to the signal frequency, and we perform the fast Fourier transform, you'll see the frequency information spread as a result. And this would result in the phenomenon known as spectral leakage. So once you have that explanation in particular, that basically answers question 1. And reducing it in practice, what you tend to do is that you want to use windowing functions to minimize spectral leakage. And one thing to note is that even though you use the windowing function, is that it will never eliminate spectral leakage, it can only mitigate it. And spectral leakage mitigation when using the window function is that you start with the sample signal here, which is x of n, and then you multiply this by some window function w of n to get the new signal, which is going to be x of w of n. I believe question 3 or 4, question 3 in particular, we're going to actually see a practical application of this. Right, so that's it for question 1. Question 2 is where we're going to be talking about the Harmon window and the rectangular window and so forth. This is actually straight from the lecture notes. So this is like when we have the rectangular window and we see the effect here for the main lobe and the side lobe. And the same thing like when we're going down here with respect to the triangle window. And we have the general shape and then the frequency response of it and so forth. So basically all the windows actually are already plotted in lecture 9 here. And what you want to observe is actually the frequency response for each one of these windows. So like for instance, the rectangular window, because of those sharp transitions, because of the rectangular shape, you'll see that the relative side lobe attenuation tends to have some magnitudes here for the side lobe frequencies. So you want to be like observing here in particular to see, okay, for the first harmonic and then for the second harmonic and so forth, you still have some magnitude here, even though it's attenuated from the main lobe magnitude itself. But when you start moving to like things like the rectangular window and so forth, sorry, from the rectangular, when you move from the rectangular window to the triangular window, you will see that when you start watching the side lobe attenuation, it tends to mitigate even further. However, because the base width here is increased, that means the main lobe width here is also going to be increased as of such. So this main lobe width that we see in here going from 0 to 0.2 is a result of this wider base lobe width here for the triangular window. If we go back to the rectangular window, we can see basically here that the rectangular window, because the width of it at the base is smaller, the main lobe width here is actually going to be smaller as well. So those are the effects actually you want to be observing while you're going on with respect to using the explanations for any of one of the windows. You want to explain that how the side lobe attenuation is going to be decreased, but at the same time, the main lobe width is going to be increased because of the base of the window here being increased. All right, so in using one over the other, what you want to make sure in particular is that it will depend on the type of application. So maybe that in a certain application, you still need some of the side lobe frequency information, but it needs to be such that it doesn't interfere with the original signal. In such a case, the rectangular window will be okay to use. You may go to like the triangular window depending on the level of attenuation and so forth. What I will say is that you just want to maintain only the main lobe information and you don't care about the side lobes, so you don't care about the harmonics. then you'll move on to things like the Harmon Window and Hannon Window and Blackman Harris and so forth. Because in those cases, the side lobes here basically are just going to be mitigated altogether. One thing to note though is that even though we have normalized frequency here, remember this normalized frequency still maps back to our actual frequency. And we've seen it in range here between 0 and 1, but this frequency is going to map back to actually what we refer to our sampling frequency and so forth. So what we want to pay attention to is that this main lobe here is going to have a range of frequencies. And those range of frequencies have to be important to what frequency information you're trying to capture. So this will basically translate to the range of frequencies you're trying to capture. And you don't want any frequencies outside of this to be captured or to be interfering with your system itself. So I hope that answers your question. Yes? No? Maybe? Alright, cool. Alright, so that should answer question 2 overall and so forth. Question 3 here, what we're going to be watching the 8-point window of your choice to the sequence given in problem set 2A, question 7, and to repeat the question, and if there's any improvement in the results. So we're going to actually do this using Octave. This computer does not have Octave installed, so I'm going to be using Octave Online here. So Octave Online here actually could actually give me the signal and so forth. We're actually going to be using this to compare our results as of such. So the original signal, which was X here, was 0, 0.944, negative 0.623, negative 0.532, 0.974, negative 0.112, negative 0.901, and 0.707. All right, so let me just verify that. Okay. Yeah, that does have some benefits. It also has some drawbacks. All right, so we have our base X of signal here, right? And then we can do FFT of X here. So let me map this to actual variable, FFT of X. So we basically get our values here, which are going to be our FFT values that if we did a long arduous process, if we did manually and so forth, right? But we want to actually be doing this with respect to comparison. And the actual calculation process, which we did in the last tutorial, was more important in that last tutorial than this one. All right, so the question here asked for, let's make sure, it asks for us to use an 8-point window of your choice. So the window that I'm going to be using here is going to be the Harmon window. So we're going to say W here. Okay, no, first I need to set up a range. So N is equal to 0 to 7. All right, so the range is set up. Let's say W of I wonder if I had a zoom button on my side. Yes, I do have the zoom button on my side, but if once you guys could control it on your side, that's fine too. Because I don't want to control it and actually see it zoomed in too much or whatnot. Everyone have their own personal preferences. Alright, so that should be set up there. Then this might complain at me because I'm starting at 0. So the Harmon window is 0.54 minus 0.46 multiplied by cosine of 2 by pi by n divided by n minus 1, which is supposed to be 7. Yep, of course they're going to complain. Alright, so let's actually do this a little bit manual. N equal to, so let me just verify one thing here to begin with. 54 minus 0.46 multiplied by cosine of 2 by pi. No, will it be just 0? Right. Then if I put it here with 2 by pi divided by 7, no, divided by 8. Alright, okay, so we should be set there. Make sure I have the equation correct. Number of frequency components. Right, okay. Which should be set there. Okay, right. So that's the equation I need to use. Right, so in this case, okay, right. I know what I need to do. There we go. Okay, so the equation that we tend to use here for the Harmon window is going to be W of k is equal to 0.54 minus 0.46 cosine of 2 pi k divided by n minus 1. Now, n is the number of samples that we're required to take, and k is going to be the number of frequency components, right? So basically, if we took an 8-point window here, the n minus 1 here is basically going to be 8, regardless. So that equation here, even though you're seeing n is the number of samples you're taking, even though you say n minus 1 here, it's actually going to be divided by 8 here only for the 8 samples. So actually, this is not supposed to be n minus 1, it's just to be divided by n. So that's one thing to fix regarding to the slides. K here will go from 0, if K can highlight, okay, not be even. Right, yeah. K here will go from 0 to 7 accordingly. So, and plotting this in Octave, what basically I did here is that I set up my n range. So I said n was going from 0 to 7. So this will be from 0 to 7 here. And then my W range, because we can't start at 0 here, is that we're going to have n plus 1 here to represent the indexes starting from 1. But we'll still be using the actual value here for what we're referring to. So this will be n0, n1, n2, and so forth. So that actually will plot out all the values that I need accordingly for my W vector itself. Anyone have any questions regarding that? All right. So if you notice here, this basically only has 1, 2, 3, 4, 5, 6, 7 values here, right? We need to make sure that there's an 8th value that's going to be here. Because if you notice that these values basically are a reflection of each other as we keep on going. So this is the center point here. And then this value will be reflected. Yeah, it's 8 values. We forgot to calculate for 1. Because we only have 7 values here. Remember, this is because I do the trickery with the index. So this index will only go up to W of 7 accordingly. And I won't get the 8 values. Oh wait, no, yes, it actually is 8 values. Oops. My problem. My bad. 1, 2, 3, 4, 5, 6, 7, 8. Alright, yeah, it actually is 8 values. Okay, no problem. Alright, so we should be fine. 1, 2, 3, 4, 5, 6, 7, 8 values. Right. Okay. Yeah. Okay. Yeah, we're fine. So 1, 2, 3, 4, 5, 6, 7. Right. Okay. Yeah. So we do actually have the 8 values. Alright. So I don't have to worry about the trickery anymore. Yeah, I did it correct. Alright. So I plot the n vector. I got my 8 values here, because I made sure we need to start at the W index of 1. And we made sure that each value here was plotted accordingly, and so forth. The next step is that we want to get x of W, which is going to be x dot star W. And the dot star basically means element by element multiplication. So xw here will give us our window function values here accordingly as well. Just to verify one thing. Just to make sure all of operations were correct. Plus 0.56. Okay, so other operations do matter. No, 0.54. Oops. Okay, other operations don't matter. All right, so that's fine. Right, so because we had the x vector and the w vector, and using Octave or MATLAB, to get each one of those elements to multiply with each other with respect to each of the positions, use the dot star command. So you'll basically say x here, which is our original value, dot star by the window function. And xw, which is our results, will give us the compilation of all the values here. If we took our original x signal and we multiply it by the window signal itself. The last step is to get the FFT of this. So I'm going to say xw of xw underscore FFT is equal to FFT of xw. And at this point, we actually have our actual fast Fourier transform for the entire thing. Now, we want to compare this to xFFT, right? So in comparing this, what we can see here is that the XW FFT signal here, when we watch it for our center, or DC signal, sorry, we can see that for the XFFT here, the center signal, which will be the first component or a DC signal, we had a huge spike here because of the incorrect sampling. But when we use the XW FFT here accordingly, we can see here that this mitigates close to actually 0. which will actually reflect to the way the sampling point actually is supposed to be. When you start watching our side lobes here, so this side lobe here is supposed to match with this side lobe, we can basically see at this point that these side lobes here, whereas in the original XFFT signal, they tend to be huge. These side lobes here in the X window FFT signal tend to be more mitigated towards the end. And as we start approaching towards the center value, because remember the center value here will be the next DC value, so this will actually be our main lobe. We can see here that the main lobe here is in the window signal is more mitigated accordingly with respect to the actual main lobe here for the improper sample signal, which was being the XFFT here. So in comparison to this, what you actually see, the question was asking, is if there was any improvement in results. Yes, there actually was an improvement in result because how the X signal was incorrectly sampled, for those incorrect sample points, we now have a better representation of what the values of those incorrect samples actually are going to be, instead of these incorrect values here accordingly. Alright, so recapping what I did for this question. I have to go back a little bit. Right. So the first thing I did here is that I plot the X vector accordingly. I then found the FFT of it. Right? So I had this to set up for comparison. The next step was to set up the range for n for using the window function. Once we had that, we set up the window function accordingly. So we know that our window function is going to be 0.54 minus 0.46 multiplied by cosine of 2 pi k divided by n. So in this case, it will be such that k will be going from 0 to 7, which is our n vector here accordingly. And capital N will be 8, representing the amount of values we have here. Because we're using Octave or MATLAB, we can start at the 0 value for our indexes. So we need to make sure that this index always starts at 1. So that's why we have W of n plus 1 here. So once this is set up, we'll get all our W values here. And then the step after that would be to calculate the multiplication of the two vectors accordingly using element by element multiplication. So that actually is going to be x dot star of w to give us our x of w. So x of w here will give us our completed values when we multiply the x values and the w values across each other. And then the last step would be to get our FFT of xw. Now once we have the two, being the xw FFT and the xFFT, oh, that's handy. Right. So xFFT. We then compare the two values to realize that because the xFFT was sampled incorrectly, we have incorrect magnitudes for each one of the sampling points, and the XWFFT tends to give us a more accurate representation of what the magnitudes are for regards to this sampling points accordingly. Right, any questions regarding this? So let's see. Problem set 2A question 7 basically told you that it was sampled incorrectly. So yeah, that was given to you. If you're asking visually how you know if a signal is sampled incorrectly, what happens is that when you actually watch the spread of the frequency information and you actually plot it, you will actually see that instead of having a nice smooth transition, you tend to have rough transitions. So in using the win-win function, it tends to smooth out or spread the frequency information accordingly for you to get these nice smooth transitions. Right. Any other questions regarding this? Yes, no, maybe. So with respect to exams, what we'll do is we'll give you the window function. So we'll actually give you the equation for like W of n to use. Just remember that if you're using it and you see the function, so like in this case, I'll pull back up the PDF so I can explain it to you. So remember, you might see the equation here in this form, right? Which is W of k equal to this and so forth, right? And you might get the equation as 2 pi k divided by n minus 1, right? What you want to make sure is that even if you see it in this form, n minus 1 here actually not supposed to be n minus 1, it's actually supposed to be n. So basically we say an 8-point window, this denominator here must be 8. K here will start from 0 and go up to n minus 1. So that's the only correction for this slide. Do I have a tool here to correct this? Yes, so for any other method or any other window that you're using, the final result will be the FFT of x dot star w, where w will be any one of those functions. Not all the time x of w of FFT will give you more accurate amplitudes, but it will tend to approach more towards what the actual amplitudes are. There will be some rare cases, like if you'll be using it for a real-time signal where the frequency is unknown, or for any aperiodic signal, where that you may not always get an accurate representation, and then you'll have to be trying different windows depending on the type of application you'll be using. So in practice, it depends on the application which window is going to perform better accordingly. And I think like when you start doing research and so forth, you'll actually start seeing particular things where certain windows are better for different types of applications. So like for instance, I think for audio, you'll use more Harmon and Hannon. They may use Blackman or Blackman Harris depending on the type of audio and so forth. Draw in markups. Here we go. Not that. That could disappear. So n here will be, let's see this one time. Okay, now we'll see that after. All right, so n here will be the denominator for the Harmon window. It'll be 2 pi k here, where k going from 0 to n minus 1. All right. So that should be set regards to question 3. Question 4, which is going to be the final question that we're doing, is actually how we calculate for inverse fast Fourier transform. So we're actually going to be starting off with the results that we obtained from doing the last problem set. We're going to be testing it on this. We don't do inverse fast Fourier transform because I didn't teach you guys how to do that, but because the problem set is asking for it, I actually need to show you guys how to do it regardless. So I actually have an idea in case we encounter it in actual application. So in this case, alright, so I need a prop here to actually start this. Alright, so no, inverse fast Fourier transform will not come in the exam. I can tell you that up front. At some point, I will have to do some kind of exam prep lecture so you guys actually have a faint idea of what will be coming on the exam itself. Alright, so because I have these props here, actually this speeds up a lot of things that I'll have to explain to you guys. So I'm setting up the signal here because this was the output of the FFT that we obtained only. So it's really XFFT here. So I'm setting this up accordingly for XFFT. And we're actually going to be using this to go in reverse to get back on X's. And I'm putting X here to show you what the actual signal is here accordingly. Right, so let's set up our props here accordingly. And we'll actually start performing the inverse fast Fourier transform. So this here should be 0.6488, 0.11486. This one here will be 2.948. 0.657. If a question like this tends to come for exam, not the inverse fast Fourier transform, or actual fast Fourier transform, it will be that you need to calculate it for one stage only. So it might be like, okay, you might need to calculate the output at the third decimation stage, and in this case, we might give you the input here to work with. So it might give you this input here and just further calculate out for the final stage. Because if you actually have to do a fast Fourier transform fully in the exam, you might take about like an hour to actually complete it. Because you have no assists in the exam to actually help you out. And this should be minus 1.557. 2.5968. Alright, so this one is plus. Yeah, if a question like that comes, it'll just be for the final stage. Another thing is, like, if a question comes for you to actually get to the win-win function, it may be just that you need to calculate for xw. So we'll give you the x signal, we'll give you the window function, and ask you just to calculate for xw only. Mm-hmm. 0.4074. 2.498. So this one is minus. Hey, you could disappear. Right, so that plus that. plus 0.657, and the last one 0.6488 plus 0.1486. Right. Okay, so this block here represents the output of the fast Fourier transform for x. And we will actually be doing the process in reverse, which is the inverse fast Fourier transform, or IFFT, to actually see how we can get back to x. So what happens here is that in doing the calculations for these, you basically end up getting a set of simultaneous equations. So if we actually watch the output here for this one and this one here accordingly, because it's actually been mapping accordingly to each one of these calculations, we can see here that this one is going to be E naught, which is going across here, and then plus O naught, W8 of naught here, multiplied by that O naught, I'm going across here to give us 0.457. Similarly, for the next half of the butterfly, we'll see that this is going to be E naught here going downwards to the 1.557 part here, plus O naught multiplied by W8 of naught here, but we have this minus 1 here currently. So this actually is going to be E naught minus O naught W8 of naught. And that is going to be equal to negative 1.557. So pull up our Word document to assist with this. Put you one side, put the documents here. Alright, so let's actually start inserting equations so we actually could see this, maximize this up a little bit. Alright, good. So our first equation, when we watch it, here is going to be E naught plus O naught multiplied by W8 naught is going to be equal to 0.457. Let's copy that. Then we're going to have, for the second half of the butterfly, which is E naught minus O naught W8 naught, is going to be equal to negative 1.557. And we basically see here that E naught and O naught, because we have two equations, is actually set up as simultaneous equations. So as we keep on going for each one of these, so I'm going to do it for one more so you guys actually can see what I'm referring to here. So I'll put in this here. So this one here will be E1 plus O1 W8 1 is going to be equal, so this is actually E1 here and O1 here, W8 1, so E1 here will be going across to this value, and O naught here, W8 naught here will be going across to this value here. So the addition of the two here will be 0.6488 minus 0.1486G. Just copy this. And then the difference of the two, which will be the next half of the butterfly, will be equal to this value here accordingly. Because we can see E1 here will go down to this value, and then O1 here, W8 1 multiplied by negative 1 here. So that means E1 minus O1 W8 1 here is equal to this value here. that'll be negative 2.5968 minus 0.4074 G. And we can keep on going for each one of these to get simultaneous equations as such. So eventually what will happen here is that when we start solving for each one of these values here, and we start solving this regarding the system of simultaneous equations that we start getting here, we'll resolve out all the E values here and the O values here accordingly. So basically it's just a series of simultaneous equations you need to keep on doing, because how the butterfly is formed is basically you'll get for the addition of the two being mapped accordingly to one value, and then the subtraction of the two will be mapped to the next value here accordingly as of such. So in setting up all those simultaneous equations and solving for them, you'll see here that the first value here will work out to negative 0.55. The second value here will go down to negative 0.974 minus G 0. Okay, let me do this thing correct. Negative 2.78 G. This one here will go to 2.498. Don't know why that got so small, but leaving it for now. 0.974 plus G 0.778. Yep, we just solve for the two and we keep on going. So remember here, when we actually start watching the butterfly equations, we'll have the addition of the two values here equal to one of these values, but the subtraction of the two values here equal to the next one of these values. So this E0 value here plus the O0 W81 will give us this value. And then E0 here minus, because I'm just negative 1 here, O0 W80 will give us this value here accordingly. And because we have these two equations here with respect to E0 and O0, we can solve for E0 and O0 accordingly using simultaneous equations. So this next value here will be 1.007. This one here will be 1.06 plus 1.239 G. This one here would be 0.657. And this one here would be 1.056 minus 1.239 J. Alright, so in solving for these, what you're going to notice is that you're going to have some sort of level symmetry as you keep on going. So these DC values here that you obtain are going to be unique while you're solving for them. But the values surrounding the DC values, you're going to see some symmetry according for them. So it will be the real part here will maintain the sign, but the imaginary part here for the next half will be flipped. So this one is plus the imaginary, but this one here is going to be minus the imaginary. Same thing for the one on top here. This one here being negative imaginary, this one here is going to be plus the imaginary. Oh, oops, this one is minus that. Right. So the real part for the imaginary values will remain the same, no matter what. But the imaginary part, the sign will flip accordingly for the next half of it when you're calculating. So that's a good indicator for you to notice if you're on track when you're solving for them. So typically an inverse fast Fourier transform question will only come on the midterm, and this tends to be like a 60-mark question like a fast Fourier transform. Yeah, we wouldn't be doing this because I didn't teach you guys this up front. It's just for you guys to get an idea of how to actually do it in case you encounter it. But if a question like this comes, it will only come in the midterm. A question like this cannot come on the final. Because by the time you start solving those simultaneous equations, you'll be eating up a lot of time accordingly. Alright, so let me set up this accordingly. When we 12, it will be 24 simultaneous equations. Because 8 equations per stage. And you have 3 stages. So yeah, 24 stages, 24 equations. So let's say that 0.974 minus J 0.278J 2.498 9.974 plus J 0.78. Yeah, his AP is only 12. Yeah, we're working back all the way to the original values. So this is actually to show you, like, if an inverse fast Fourier transform question came, this is how long you actually would have been spent trying to solve for this. .7 1.056 plus 1.239G 0.657 minus 1.239G. Right. Okay, so this is actually when we have the second decimation stage. So the input here for the third decimation stage, which we can see here, serves as the output of the second decimation stage. So once we have this output here, and we have the Fourier transform parts set up here according for the butterfly diagrams, it's basically the same thing we're going to be doing again for solving it. So to give you an idea of how this tends to get a little bit cumbersome, because we're at the second decimation stage. So I want to show you guys for one of these simultaneous equations that we need to solve for. So put you there. So this was to deck. This is going to be the second deck. Right. So let's actually watch what happens here as we keep on going with respect to this. So E naught here will be going towards this value and this value here only. So we'll do the addition part first. So E naught will be going towards this value plus E O naught. Yeah, the command for inverse fast Fourier transform is IFFT actually. So E naught will be going towards this value here, and then the addition of E O naught multiplied by W4 naught will result in this value. So the equation here is going to be E naught plus E O naught multiplied by W4 naught is equal to negative 0.55. And then similarly, the difference between the two is going to be 2.498. Yes, that's 110. Yeah, just a different naming convention. You can use your own naming convention if you have to solve for this. You don't have to use this actual naming convention. So, in solving for this, what you end up finding out is that, as we keep on repeating here, EE naught here can end up being 0.974. And then EO naught here is going to be negative 1.524. And then if you keep on doing this for EE1, EO1, and then the next pair will be OE naught, OO naught, OE1, and OO1, you actually resolve all the equations using the same simultaneous equation method, and you actually start getting all the values extracted out. So this one here will work out to negative 0.974. EO1 here will work out to 0.278. OE naught will be 0.832. OE1 will be 1.056. OO naught will be 0.175. And OO1 will be negative 1.239. So the same simultaneous equations that you'll be using throughout, because you're just watching how the butterfly diagram is mapped, and I'll just be using the simultaneous equations to solve for each one of those terms there on the left-hand side accordingly. Okay. So the last part is where we take the input here for our second decimation stage, and we map this to the output of the first decimation stage here accordingly. So let me actually set this up, 0.974, negative 0.974, negative 1.524, 0.278, 0.832, 1.056, 0.175, negative 1.239. Alright. And each one of these terms here, so let me say refer to this as x0, x1, x2, and x3 and so forth. So x0, say this one was x1, x2, x3, x4, x5, x6, x7. Alright, so let's split this back so I actually can show you how this actually solves. This will be a first decimation stage. Insert the equation. Right. So if you actually watch how the butterfly output is here, we'll basically see that x0 here goes to this output, 0.974, and x1 here, the addition of the two, will give us this. So this will result and x naught plus x1 is equal to 0.974. And then the next half of the butterfly diagram, which is going to be x naught here, going towards here, and then x1 here, but minus 1 will give us this value here. So it's going to be x naught minus x1 gives us negative 0.974. And just to highlight the process for x2 here and x3 here. So the summation of x2 and x3 will give us this value here, 1.524, sorry, negative 1.524. And then the difference between the two will give us 0.278 here. Right. So you can keep on doing that and so forth. And eventually, what would happen is that x naught here will work out to 0. x1 here will work out to 0.974. x2 here will work out to negative 0.623. x3 here will work out to negative 0.901. x4 here will go to 0.944. x5 here will work out to negative 0.112. x6 will work out to negative 0.532. x7 will work out to 0.707. Now, the last step here is that we need to bit reverse in order to get it back into the actual sequence what x of n is supposed to be. So, to give you an idea of what's going on here, remember that these values here were reversed accordingly in order to set up for the butterfly diagram. So, the position of this value here, if you watch it in binary, is 0. But the position of this value here, when you bit reverse this, is actually going to be 4. Because, see if I can set a text box here to give you guys an idea what's going on. So, this position here would be 0, 0, 0. But then this position here originally would have been 0, 0, 1. But because this is the bit reverse position, and this means that the first and last bits were swapped, this now is 1, 0, 0, which will give us 4. And similarly, this position here will be 0, 1, 0, so this position is unaffected. Put you one side there. But this position here would have been 0, 1, 1. And because we bit reversed, that means this is now 1, 1, 0, which is position 6. So we need to actually pay attention to what these actual positions are as we keep on going So I'll complete it to give you guys of what's going on here. So this one here will be in 0, 1, 2, 3, 4. So it'll be 1, 0, 0. But because we bit reverse, this is now 0, 0, 1. This one here, this will be position 5, so this will mean 1, 0, 1. Bit reversal doesn't affect this, so this remains the same. This one here will be in position 6, so this will mean 1, 1, 0. But because this is reversed, this now becomes 0, 1, 1. And our last one here will be position 7, which will mean 1, 1, 1. And this is unaffected. And when we do bit reversal, okay, accordingly. So once we bit reverse these, we'll get back the original sequence that we require. And the original sequence would be when we go back in Octave here. Will be in this form here of X, which will be the starting sequence that we had from the original question. To answer the command for inverse fast Fourier transform, the command is just IFFT, and you just put in the fast Fourier transform here accordingly. IFFT, XFFT, undefined a line 1,6. Alright. Say X on 4. Oh, because it's undefined. Alright, cool. Where are we? I lost the session, so put back in the X. X FFT is equal to FT of X. Then if I do IFFT of FFT of X, oh, whoops. X underscore FFT, I'll get back the original answer here accordingly. Comparison is the same. Alright, so in the event that you ever get focused on an inverse fast Fourier transform question and you don't have a computer to assist you, the method used is basically a whole set of simultaneous equations. And it tends to get very long and annoying with respect to how many decimation stages that you'll have to do accordingly. If you have access to actual computer, you just perform the inverse fast Fourier transform function and you just get back the original sequence accordingly. But the purpose of the question was for you guys to actually see how to do it manually in case you encounter it. Alright. And then question 5 here and question 6 were basically just to use the PowerSpec-D MATLAB file that was provided on myELearning, and just to actually observe how the signals here will actually be manipulated accordingly, and how you actually can observe the power spectral density as well. Okay, so that basically is the end of the tutorial session. Anyone who has any further questions? On your final exam, what you'll tend to get more like is like how the questions tend to repeat. So from previous years. So you might want to watch in particular like how actually do we calculate for XW. So a question may come where we give you an input sequence X, and then we give you the window function in terms of the equation, and then we ask you what is going to be x of w, being the multiplication of x and the window function. If a fast Fourier transform question comes on the exam, it will just be only for one decimation stage only. So you'll get the input towards the decimation stage, and then you just have to calculate the output only for that decimation stage. The inverse fast Fourier transform will not come on the exam accordingly. I just showed you guys how to do this in the event that you actually have to do this in a real world application. And if it was coming, it will only come on the midterm, because to do all those equations and so forth, it eats up a lot of time. And it's not practical to do this in a final exam. Question that may come regards to like the window function tends to be about 10 to 12 marks of the 100 marks on the final exam. The fast Fourier transform decimation stage may also be like a 10 mark or 12 mark question accordingly. Any further questions? All right, so hopefully I should have YouTube up and running by next class, but if you guys want to use Blackboard Collaborate, I can always use that. That's not an issue. What I would try to figure out is how I grab a new recording from here and to upload onto the YouTube channel for data viewing. And hopefully that should be easy enough to do. If not, we'll just go straight to YouTube, because YouTube does all the recording for one time and it pushes straight onto the channel. Next class should be next week, Tuesday, around the same time. We will be doing problem set 3, I believe. Yeah, we'll be doing problem set 3. I'll pop a forum notice, just a reminder for when we're actually doing that tutorial as well. Yeah, because Blackboard Collaborate, because everyone is using it right now all over the globe, and the servers are being overwhelmed. So I rather use YouTube because they have better server resources. Like I say, I'll just see if I can grab the recording and post it on YouTube, so that way whoever who wasn't able to attend the Blackboard session can actually view it on YouTube, and they could just email me and ask me any questions accordingly. Actually, I did not see that as yet. I was supposed to watch it. Once I watch it, I'll figure out what goes on with regards to it. I suppose they're probably using probably spatial mapping with the fast Fourier transforms in order to achieve the 3D sound effect. I could be wrong. Until I watch it, I'll know for sure. Alright, so basically we're done here, and if you have any further questions, email me, post it on the forum. I'll answer you guys accordingly. Yes, I'll upload more recent past papers on myELearning sites. I just have to pull them accordingly. I'm supposed to have probably up to 2016 or 2017, which I can actually put up on the website itself, on myELearning.